June 27, 1943, Rechlin Luftwaffe Test Center, Mecklenburg, Germany. Oberingenieur Klaus Diesel's hands moved carefully across the complex mechanism before him, examining what German aviation engineers would later acknowledge as the most sophisticated analog computer they had ever encountered. The device, recovered 3 weeks earlier from a crashed American bomber near Kiel, weighed 23 kilograms and contained over 2,000 precision-machined components working in mechanical harmony that German optical instrument makers, despite their world-renowned expertise, admitted they could not replicate. This is impossible precision for a field-deployable military instrument. Our best laboratory equipment cannot hold tolerances this fine under combat vibration. 24 hours earlier, recovery teams had delivered the mechanism to Rechlin, following its extraction from a Boeing B-17 Flying Fortress that had gone down during a raid on submarine construction yards. The aircraft, part of the United States Army Air Force's 8th Air Force, carried equipment so secret that bombardiers had been ordered to destroy it with thermite grenades before bailing out, or in the event of forced landing in enemy territory. Those destruction protocols had failed. German recovery teams found the bombsight largely intact, its gyroscopes still spinning freely, its complex gearing system undamaged. What German engineers discovered when they examined that device would expose a technological achievement so extraordinary that it would force Luftwaffe leadership to confront an uncomfortable reality. The Americans had not merely built a better bombsight, they had created an analog computing system that processed ballistic calculations in real time with accuracy German technology could not match. The capture of this single instrument would reveal that American precision, optical engineering and mechanical computation had advanced years beyond anything Germany possessed. They were not fighting the same technological war. They were years behind in understanding how to manufacture precision instruments at industrial scale while maintaining tolerances measured in 10,000ths of an inch. The story of this technological achievement began not with wartime urgency, but with a decision made during peacetime by a civilian engineer obsessed with solving an impossible problem. In 1928, Carl Norden, a Dutch immigrant engineer working in New York, had partnered with the United States Navy to develop a bombsight capable of hitting targets from high altitude with unprecedented accuracy. Norden was not a military man, but a precision instrument designer who had worked for Sperry Gyroscope Company before establishing his own consulting practice. His approach to bomb aiming reflected an engineer's conviction that mechanical precision could solve problems others considered fundamentally unsolvable. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The fundamental challenge of high-altitude bombing seemed straightforward, but concealed extraordinary complexity. An aircraft traveling at 200 miles per hour at 20,000 feet altitude needed to release bombs approximately 1 mile before the target to account for the bomb's forward velocity and the time required for them to fall through 4 miles of air while being affected by wind, air density, and the aircraft's motion. Calculating the precise release point required accounting for multiple variables simultaneously: ground speed, altitude, wind direction, and velocity at multiple altitudes as the bomb fell, air temperature affecting air density, the ballistic characteristics of the specific bomb type being dropped, and the aircraft's drift angle if flying with crosswind component. Human bombardiers attempting these calculations, manually using mechanical calculators or slide rules, could rarely achieve accuracy better than several hundred feet under ideal conditions. Under combat stress, with anti-aircraft fire and fighter attacks, accuracy degraded dramatically. Pre-war bombing tests conducted by the United States Army Air Corps showed that even experienced bombardiers missed designated targets by an average of 1,200 feet when bombing from 15,000 feet altitude. This level of accuracy was adequate for attacking large area targets like marshalling yards or industrial complexes, but entirely inadequate for precision strikes against specific buildings, bridges, or ships. Norden approached the problem not as a tactical challenge requiring better trained bombardiers, but as an engineering challenge requiring better instruments. His insight was that mechanical systems, if designed with sufficient precision and sophistication, could perform ballistic calculations continuously and automatically with accuracy no human could match. The device he designed, which would undergo continuous refinement from 1928 through 1945, represented one of the most sophisticated mechanical analog computers ever created. The Mark 15 Norden Bombsight, the version in widespread operational use by 1943, consisted of two main assemblies working in coordination. The stabilization platform used a gyroscope system to maintain a stable reference frame independent of the aircraft's motion. Aviation gyroscopes were not new technology. Germany had used them extensively in aircraft instruments since World War I. What distinguished Norden's stabilization system was its extraordinary precision and the sophistication of its mechanical integration with the computing mechanisms. The gyroscopes, manufactured to tolerances measured in 10,000ths of an inch, maintained their orientation despite aircraft vibration, turbulence, and maneuvering. The stabilization platform provided the reference frame from which all other measurements were made, essentially creating an artificial horizon that remained perfectly level regardless of how the aircraft moved around it. The analog computer assembly performed continuous ballistic calculations using mechanical components, differential gears, precision machined cams, and interconnected mechanical calculators. The bombardier input variables including altitude, airspeed, wind direction, and velocity, and bomb type. The computer then continuously calculated the precise release point, updating its solution 30 times per second as conditions changed. The system was not simply a calculator that produced a single answer. It was a continuous computing mechanism that tracked the aircraft's position relative to the target and determined the exact instant when bombs should be released to achieve impact at the desired point. The most revolutionary aspect of the Norden system was its automatic pilot interface. Once the bombardier had identified the target and input the necessary data, the bombsight actually flew the aircraft during the final bombing run. The system sent control inputs to the aircraft's autopilot, making small adjustments to heading and speed to ensure the aircraft followed the precise trajectory the computer calculated as necessary for accurate bomb release. The bombardier did not manually fly toward the target while trying to line up crosshairs. The bombsight flew the aircraft automatically along the computed ballistic path, released the bombs at the calculated instant, and only then returned control to the human pilots. This level of automation was unprecedented in military aviation technology of the early 1940s. German aircraft used autopilots for reducing pilot fatigue during long-range flights, but these systems simply maintained heading and altitude. They did not perform navigation or weapons delivery functions. The concept of an instrument that simultaneously computed ballistic solutions and controlled the aircraft to execute. Those solutions represented a fundamental advance in human-machine integration that German aviation engineers had not seriously pursued. The precision required to manufacture Norden bombsights pushed American optical instrument manufacturing to new levels of sophistication. Carl Norden's company, Carl L. Norden Incorporated, located in New York, developed specialized manufacturing processes specifically for bombsight production. Components were machined on precision lathes and milling machines that were themselves manufactured to extraordinary tolerances. Gears were cut using specialized gear-cutting machines that could maintain accuracy of plus or minus 0.0005 inches across the entire gear tooth profile. Optical elements were ground and polished using techniques adapted from astronomical telescope manufacturing, achieving surface finishes and optical qualities that eliminated distortion even at high magnification. The gyroscope assemblies required particularly extreme precision. The gyroscope rotors were balanced so precisely that they could spin at thousands of revolutions per minute for hours without detectable vibration. The bearings supporting these rotors were manufactured from specially selected steel alloys, hardened through precise heat treatment processes, and finished to surface smoothness, measured in micro-inches. Each bearing was individually tested and selected for minimum friction and maximum durability. Assembly of complete bombsights occurred in temperature-controlled clean rooms where humidity and dust were carefully regulated. Skilled technicians, many of whom had trained for months to learn the specialized assembly procedures, put together each unit by hand. Every component was inspected multiple times during assembly. Completed units underwent extensive testing, including simulated bombing runs in ground-based trainers that replicated aircraft motion and vibration. Production quality control was extraordinarily rigorous by the standards of military manufacturing. Approximately 10% of manufactured components failed to meet specifications and were rejected during inspection. Even among components that passed inspection, units were selected and matched to ensure optimal performance when assembled together. A gyroscope rotor that met specifications but was slightly out of balance would be paired with a housing that compensated for that specific imbalance. This level of selective assembly was common in laboratory instrument manufacturing, but highly unusual for military equipment intended for combat deployment. The result of this manufacturing sophistication was a bomb sight that functioned reliably under combat conditions while maintaining accuracy that seemed almost impossible given the mechanical technology of the era. Under optimal conditions, with experienced bombardiers operating properly calibrated equipment, the Norden Bombsight could place bombs within 75 feet of the aim point from 20,000 feet altitude. Even under typical combat conditions, with less than perfect visibility and moderate anti-aircraft fire, experienced bombardiers achieved accuracy of approximately 200 feet, roughly 1/6 the accuracy of pre-Norden manual bombing techniques. Security surrounding the Norden Bombsight reflected the United States military's understanding of its strategic value. The device was classified at the highest level of military secrecy. Bombardiers were required to take an oath, swearing they would protect the bombsight with their lives. During training, bombardiers learned bombsight operation in secured facilities where guards prevented unauthorized personnel from observing the equipment. The oath ceremony, which occurred before bombardiers were allowed to train with actual Norden equipment, included dramatic language, emphasizing the bombsight's importance to the war effort and the bombardier's personal responsibility to prevent its capture. In operational deployment, security procedures were extensive and strictly enforced. Bombsights were stored in guarded vaults when not in use. Before each mission, bombardiers signed for their assigned bombsight, accepting personal responsibility for its security. During flight, the bombsight was covered with a canvas shroud, whenever not in active use to prevent observation even by other crew members. If capture seemed imminent during forced landing or bailout, bombardiers were required to destroy the bombsight using thermite grenades specifically carried for that purpose. The thermite grenades, which burned at temperatures exceeding 3,000 degrees Fahrenheit, could reduce the bombsight to molten metal in less than 30 seconds, ensuring no useful technology could be recovered. Despite these elaborate security measures, the statistical reality of aerial combat meant some bombsights would inevitably be captured. The United States 8th Air Force, conducting strategic bombing raids over German-occupied Europe beginning in 1942, suffered substantial losses. On average, approximately 4% of aircraft dispatched on missions failed to return. Some were destroyed completely by anti-aircraft fire or fighter attacks, leaving no recoverable wreckage. Others crashed in ways that destroyed equipment through impact or fire. But some aircraft made forced landings or crashed in circumstances where equipment remained at least partially intact. German intelligence services and Luftwaffe technical units actively sought to capture American bombsights from the moment B-17 bombers began appearing over Europe. Intelligence reports indicated the Americans possessed sophisticated bomb-aiming equipment that contributed to their claimed accuracy. Luftwaffe technical intelligence, under the direction of Oberst Edgar Peterson and later Oberst Josef Schmid, established procedures for examining crashed American aircraft and recovering any valuable technical equipment. Recovery teams were trained to identify significant components and preserve them for technical evaluation. Bomb sites, identified by their location in the aircraft nose and their obvious mechanical complexity, received priority attention whenever found. The first relatively intact Norden bomb sites reached German technical evaluation facilities in late 1942. These early captures came from aircraft shot down over France or the Low Countries, where German recovery teams could reach crash sites quickly before resistance forces or local civilians disturbed the wreckage. Initial examinations, conducted by Luftwaffe technical officers with aviation engineering backgrounds, recognized immediately that the American bombsight represented sophisticated technology deserving detailed analysis. However, the first captured units were too damaged from crashes or too incomplete from successful bombardier destruction attempts to allow comprehensive evaluation. By spring 1943, German intelligence had accumulated enough information from prisoner interrogation, signals intelligence, and wreckage examination to understand that American bombing accuracy was superior to German capabilities. Luftwaffe generals watched with concern as American bombers struck targets with precision that German horizontal bombers could not match. The 8th Air Force's attack on the Focke-Wulf aircraft assembly plant at Marienburg on October 9, 1943, would later demonstrate devastatingly effective bombing accuracy, but even earlier raids showed that American bombardiers could hit relatively small targets from high altitude with consistency that troubled German defense planners. The crucial breakthrough for German technical intelligence came on June 7, 1943, during a raid on German submarine construction facilities at Kiel. A B-17 from the 306th Bombardment Group was hit by anti-aircraft fire over the target. The aircraft, piloted by First Lieutenant Robert Shaw, suffered severe damage to 2 engines and the hydraulic system. Unable to maintain formation or altitude, Shaw attempted to reach neutral Sweden, approximately 200 miles northeast. The crippled bomber made it to within 50 miles of the Swedish coast before the remaining engines failed. Shaw ordered the crew to bail out, and all 10 men successfully parachuted into the Baltic Sea, where they were rescued by German naval vessels. The B-17, now pilotless, continued flying on momentum and residual power from its failing engines. It descended gradually over approximately 15 minutes before crashing in a field near Lübeck. The aircraft hit relatively flat, plowing through farmland before coming to rest largely intact. The impact was severe enough to buckle the fuselage and destroy much equipment, but, crucially, the bomber did not burn. German military personnel reached the crash site within 2 hours. When they examined the nose compartment where the bombardier station was located, they found the Norden Bombsight still mounted in its support cradle, covered by its canvas shroud, apparently undamaged by the impact. The bombardier, Second Lieutenant James Morrison, had followed emergency procedures to some extent. He had armed the thermite grenade intended to destroy the bombsight and positioned it against the device's housing. But in the chaos of bailout, with the aircraft descending rapidly and time critically short, Morrison had either failed to pull the igniter or had pulled it incorrectly. The grenade had not detonated. When German recovery personnel removed the canvas shroud, they found themselves examining the most complete and intact Norden bombsight yet captured, a Mark 15 model in nearly pristine condition. The recovery team, following standing procedures, photographed the bombsight in place, documenting its mounting configuration and connection to aircraft systems. They then carefully disconnected electrical and mechanical connections and removed the entire unit, along with its mounting cradle. The bombsight was packed in custom-built protective crating and transported under armed guard to Rechlin Luftwaffe Test Center, the primary Luftwaffe facility for evaluating captured enemy equipment and testing experimental aircraft and systems. Oberst Peterson, informed immediately of the capture, ordered that Germany's most experienced aviation instrument specialists be assembled to conduct the evaluation. The examination team at Rechlin included some of the finest optical and mechanical engineers in Germany. Klaus Diesel, the Oberingenieur assigned to lead the technical evaluation, had worked for Carl Zeiss, the renowned German optical manufacturer, before joining Luftwaffe Technical Services in 1940. His background included extensive experience with precision, optical instruments, fire control systems, and mechanical computing devices. Also present were representatives from Carl Zeiss Jena, Askania Werke, which manufactured German bombsights, and Siemens, which produced aviation instruments and electrical systems for the Luftwaffe. Several Luftwaffe bombardiers attended to provide operational perspective on how such equipment would be used in combat. The examination began on June 27, 1943, in a secured laboratory facility at Rechlin. The Norden bombsight sat on a clean work table under bright lighting, surrounded by engineers eager to understand how it functioned and what capabilities it provided American bombardiers. Diesel began methodically, directing his team to photograph every component from multiple angles before any disassembly occurred. Detailed sketches were made, showing the arrangement of major subassemblies and how they interconnected. External dimensions were carefully measured and recorded. Even this preliminary external examination revealed extraordinary engineering. The overall package was compact, approximately 14 inches tall, 13 inches wide, and 27 inches long, yet clearly contained numerous complex mechanisms. The housing was machined from aluminum alloy with exceptional surface finish and precision-fitted covers. Every fastener, every adjustment point, every optical element showed evidence of manufacturing care that exceeded normal military equipment standards. This was not rugged field equipment designed for ease of maintenance and repair. This was precision laboratory instrumentation adapted for military deployment. When the team began careful disassembly, removing covers and access panels to examine internal mechanisms, the sophistication became even more apparent. The gyroscope assembly, mounted on a precisely machined platform, used bearings that German engineers immediately recognized as extraordinary. Diesel examined the bearing surfaces under magnification and noted their mirror-smooth finish. These bearings are finished to optical instrument quality. We do not manufacture aviation equipment to such standards because we believed combat vibration would destroy precision components. The Americans have achieved something we thought impossible, maintaining laboratory precision engineering in field-deployable military equipment. The gear trains that transmitted motion between the computing elements and the stabilization platform were equally impressive. Each gear was precision-cut with involute tooth profiles that German engineers recognized as state-of-the-art design. The gears meshed with virtually no backlash, meaning there was no lost motion between input and output. In mechanical computing, backlash introduces errors that accumulate through the calculation chain. Eliminating backlash required manufacturing precision that German engineers associated with master clocks and scientific instruments, not military bomb sites, expected to function after being subjected to aircraft vibration, temperature extremes, and combat stress. The optical system included a stabilized telescope that bombardiers used to view the target. The telescope's optical elements, multiple precision ground lenses, were mounted in a housing that allowed them to remain aligned regardless of aircraft motion. German engineers examining these optics under laboratory equipment confirmed they met specifications comparable to high-quality astronomical telescopes. The lens coatings, which reduced reflections and improved light transmission, used techniques that German optical manufacturers employed only in the finest instruments. Applying such coatings to military equipment seemed extravagant, yet the Americans had clearly deemed it necessary for optimal performance. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Over 3 days of intensive examination, June 27th through 29th, Diesel's team documented every aspect of the Norden bombsight's design and construction. They identified approximately 2,000 individual components, ranging from large castings to tiny precision screws. They traced the mechanical logic of the computing system, understanding how differential gears performed addition and subtraction, how cam followers translated rotation into linear motion, how feedback loops continuously updated calculations as input conditions changed. They tested the gyroscopes, confirming they maintained their orientation with drift rates of less than 1 degree per hour, precision German aviation gyroscopes rarely achieved. The team attempted to reassemble the bombsight after their examination, carefully replacing components in reverse order of disassembly. Despite their expertise and meticulous documentation, they encountered difficulties. Certain adjustments required specialized tools or procedures not immediately obvious from examination. Some components, when reassembled, did not function as smoothly as they had before disassembly, suggesting the original assembly had included selective fitting or adjustment procedures the German team had not identified. After hours of patient work, they achieved partial reassembly, with major subsystems functioning but overall performance degraded from the original condition. This experience reinforced a crucial reality. Reverse engineering complex precision equipment was far easier than manufacturing it. German engineers could understand how the Norden bombsight worked. They could appreciate its elegant mechanical solutions to ballistic computing problems. They could admire the manufacturing quality. But replicating it would require not just understanding the design, but matching the entire manufacturing infrastructure. Precision machine tools, quality control procedures, skilled workforce, and industrial organization necessary to produce such equipment in quantity while maintaining the tolerances essential for proper function. On June 30th, 1943, a classified conference convened at the Reich Air Ministry in Berlin. The meeting, held in a secured briefing room, brought together Luftwaffe leadership, representatives from German optical and precision instrument manufacturers, and technical specialists who had examined the captured Norden bombsight. General der Flieger Erhard Milch, State Secretary of the Reich Aviation Ministry and Inspector General of the Luftwaffe, presided over the session. Milch, who had been instrumental in rebuilding German air power during the 1930s, understood both aviation technology and industrial production capacity. His presence signaled the importance Berlin attached to understanding American bombing capabilities. Oberingenieur Klaus Diesel presented the technical findings methodically, using detailed diagrams and photographs projected onto screens. He explained the bombsight's operating principles, its mechanical computing architecture, and most importantly, its manufacturing quality. The presentation lasted nearly 2 hours, with frequent interruptions as attendees asked questions about specific technical details. Diesel's conclusion was professionally worded, but devastating in its implications. The American bombsight represents integration of optical precision, mechanical computing, and gyroscopic stabilization at a sophistication level we have not achieved in any operational military equipment. More critically, the manufacturing quality indicates industrial production processes capable of maintaining extraordinary tolerances across thousands of components. This is not experimental equipment. This is series production hardware, implying the Americans manufacture these devices in substantial quantities. The implications extended beyond the immediate tactical question of American bombing accuracy. If American industry could manufacture precision instruments of this sophistication at scale, what did that reveal about overall American industrial capability? German intelligence had consistently underestimated American military production capacity throughout the war's early years. Reports from the Eastern Front indicated American Lend-Lease equipment arriving in Soviet hands in quantities that seemed implausible given pre-war assessments of American industry. Captured American aircraft showed manufacturing quality and design sophistication that contradicted German assumptions about American technological capabilities. The Norden bombsight provided tangible evidence that these intelligence estimates had been fundamentally wrong. American industry possessed not just raw production capacity, the ability to build large numbers of relatively simple products, but also the precision manufacturing capability to produce complex, sophisticated equipment at industrial scale. This combination of quantity and quality was exactly what German war planners had assumed was impossible. You could have mass production of simple equipment, German doctrine held, or limited production of sophisticated equipment, but not both simultaneously. The Americans had apparently achieved both. Representatives from German bombsight manufacturers, particularly Askania Werke and Carl Zeiss, provided context on German capabilities for comparison. Germany's standard horizontal bombing sight, the Luftfernrohr 7, designated Lotfe 7, had been in service since 1938. The device was competent by pre-war standards, using optical sighting combined with mechanical calculation of bombing parameters. Bombardier's input altitude, airspeed, and wind data, and the Lotfe 7 provided aiming information through its optical sight. The system worked adequately for its intended purpose, achieving accuracy of approximately 400 to 600 feet from 15,000 feet altitude under favorable conditions. However, the Lotfe 7 was not an automatic computing bombsight in the American sense. It required continuous manual adjustment by the bombardier, who made corrections based on observed drift and experience-based estimation. The calculations it performed were less comprehensive than the Norden's continuous ballistic solution. Most significantly, it did not interface with the aircraft autopilot to control the bombing run automatically. German horizontal bombers relied on pilot skill and bombardier-pilot coordination to achieve accurate bomb release, introducing human factors that degraded accuracy compared to automated systems. Germany had developed more sophisticated bomb sights for specific applications. The Stuve dive bombing sight used in Stuka aircraft was elegant in its mechanical simplicity, using altitude and dive angle to compute release point automatically. But dive bombing was a completely different tactical approach, relevant only to specialized aircraft operating in specific scenarios. For horizontal bombing from high altitude, which was increasingly the primary strategic bombing method as air defenses improved and made low-altitude attack too costly, Germany had nothing comparable to the Norden bombsight. Carl Zeiss engineers explained the manufacturing challenges that would face any German attempt to replicate Norden-level precision in production bombsights. Zeiss certainly possessed the technical expertise to manufacture components meeting Norden specifications. The company's reputation for optical excellence was world-renowned. German laboratories contained precision manufacturing equipment matching anything available anywhere. But laboratory capability differed fundamentally from production capability. Building one perfect unit in a controlled laboratory environment was entirely different from building thousands of units in production facilities while maintaining consistent quality. The specific challenges were both technical and organizational. Precision machine tools capable of maintaining tolerances of plus or minus 0.0005 inches were available in Germany, but in limited numbers. These tools were typically reserved for manufacturing master gauges, prototype components, or specialized military equipment like submarine periscopes or artillery rangefinders. Using such equipment for mass production of bomb sites would require either diverting tools from other critical programs or procuring additional precision machinery. Building new precision machine tools took months and required skilled workers who were increasingly being drafted for military service. Quality control procedures necessary to ensure every component met specifications would slow production substantially. Current German bombsight manufacturing, which produced approximately 200 Lotfe 7 units monthly across multiple facilities, relied on relatively straightforward inspection methods. Implementing the selective fitting and individual component testing the Norden Bombsight apparently required would reduce production rates by perhaps 50% while increasing costs dramatically. The economic calculation was troubling. Germany could probably build Norden-quality bombsights, but at what cost in time, resources, and diversion of capacity from other programs? Material requirements presented additional obstacles. The Norden bombsight used aluminum alloys, steel alloys, and optical glass of specific types and qualities. Germany had adequate aluminum supplies through 1943, though allocation competed with aircraft manufacturing, which consumed vast quantities. Steel alloys requiring particular characteristics could be produced, but again faced competition from other military uses. Optical glass, particularly the high-quality varieties required for precision lenses, came from specialized manufacturers operating at near capacity. Expanding optical glass production would require building new facilities with specialized equipment, a process requiring years. Perhaps most challenging was the workforce requirement. Manufacturing precision instruments required skilled machinists, optical grinders, assembly technicians, and inspectors with specialized training. Germany had excellent technical education systems and traditionally strong mechanical engineering culture. However, by mid-1943, skilled workers were increasingly scarce. Men with the mechanical aptitude and training necessary for precision instrument manufacturing were exactly the same men the Wehrmacht needed for maintenance roles, technical positions, and increasingly as combat replacements as casualties mounted on the Eastern Front. The conference attendees understood they faced an impossible situation. Replicating American bombsight capability would require resources Germany could not spare from existing programs. Time Germany did not have given the strategic situation, and workforce Germany could not provide given competing military demands. Even if all resources were made available immediately, best estimates suggested German industry could not produce Norden-equivalent bombsights in militarily significant numbers before late 1944, at earliest, possibly not until 1945. General Milch, listening to these assessments, asked the fundamental strategic question: if Germany could not match American bombing accuracy, what countermeasures were possible? The discussion that followed explored various approaches, none entirely satisfactory. Improved fighter defenses could reduce American bomber effectiveness, but this required aircraft production capacity already strained beyond sustainable limits. Anti-aircraft artillery could be expanded and improved, but this consumed steel, ammunition, and trained personnel needed elsewhere. Dispersal of critical industries would reduce vulnerability to precision bombing, but decreased production, efficiency, and complicated logistics. One participant suggested that perhaps German intelligence had overestimated American bombing accuracy. Perhaps the captured bombsight was not representative of typical American equipment. Perhaps American bombardiers did not actually achieve the accuracy the Norden design theoretically enabled. These hopeful suggestions were dismissed by intelligence officers present who had compiled statistical analysis of American bombing raids. The data showed unmistakably that American bombing accuracy had improved substantially between 1942 and 1943. Specific factories, railroad yards, and even individual buildings were being hit with consistency that manual bombing could not explain. The Schweinfurt-Regensburg missions, which would occur 2 months later on August 17, 1943, would provide devastating confirmation of American precision bombing capability. The 8th Air Force attacked ball-bearing factories in Schweinfurt and Messerschmitt aircraft plants in Regensburg in a coordinated deep penetration raid. Despite heavy losses, 60 B-17 bombers shot down out of 376 dispatched. The American formations hit their targets with accuracy that caused substantial production disruption. Schweinfurt's ball-bearing output, critical for German military production, dropped by approximately 34% for several months following the raid. Post-raid damage assessment by German authorities confirmed that American bombs had concentrated on the intended targets, with minimal waste on surrounding areas. This was not area bombing of the type RAF Bomber Command employed against German cities at night. This was precision attack on specific industrial facilities, made possible by bomb sites that allowed accurate delivery despite anti-aircraft fire and fighter opposition. The strategic implications were profound. Critical German war production depended on relatively small numbers of specialized facilities. Ball-bearing plants, synthetic fuel refineries, aircraft engine factories, these were point targets that required precision attack to damage effectively. If American bombers could strike such targets accurately from high altitude in daylight, then Germany's industrial infrastructure was vulnerable in ways that defensive measures could not adequately protect. Dispersing production helped but reduced efficiency. Hardening facilities against bomb damage was expensive and limited. Fighter defenses could shoot down bombers, but could not prevent determined attacks from eventually hitting targets. The mathematical reality was brutal. American production capacity allowed them to absorb losses and return repeatedly until targets were destroyed, while German production could not be expanded fast enough to replace losses and simultaneously repair bomb damage. The June 30th conference concluded with several decisions that reflected German recognition of technological inferiority they could not overcome. First, captured Norden bombsights would be studied in detail to extract any design principles or manufacturing techniques applicable to German development. While Germany could not replicate the complete system, specific innovations might be adaptable. Second, development of improved German bombsights would continue, but with realistic assessment that matching American capabilities was not achievable in the war's likely timeframe. Incremental improvements to existing systems offered more practical benefit than attempting revolutionary advances. Third, and most significantly, Luftwaffe strategy would need to account for American precision bombing capability as an established reality that countermeasures could only partially address. This meant accelerating the dispersal of critical industries, increasing air defenses around remaining concentrated facilities, and accepting that certain production targets would suffer periodic disruption that planning must accommodate. It also meant that the Luftwaffe's own strategic bombing capabilities, which by mid-1943 were essentially non-existent, would not be revived. Germany lacked both the bomber force and the precision bombing technology to threaten Allied industrial production meaningfully. German bomber development had taken a fundamentally different path than American strategic aviation. The Luftwaffe had been designed primarily for tactical support of ground operations, with strategic bombing as a secondary mission. German bombers like the Heinkel He 111 and Dornier Du 17 were medium bombers optimized for supporting army operations, not long-range strategic attack. Attempts to develop heavy bombers, including the Heinkel He 177 and later designs, had been plagued by technical problems, production difficulties, and shifting priorities. By 1943, meaningful German strategic bombing of Britain had ceased. The Luftwaffe lacked bombers with the range, payload, and defensive armament necessary to reach British targets and survive increasingly effective RAF fighter defenses. More critically, German bombers lacked the navigation and bomb-aiming equipment necessary for accurate attack, even if they could reach targets. German radio navigation systems like Knickebein and X-Gerat had been effective in 1940 to 1941, allowing bombers to find targets in darkness and weather. However, British countermeasures, including jamming and deception, had progressively degraded these systems' effectiveness. Without accurate navigation or precision bomb sights, German bombers attempting strategic attack on Britain would have been reduced to inaccurate area bombing at night, while suffering heavy losses to defenses. The cost-benefit calculation made such operations strategically pointless. Better to conserve bomber forces for tactical missions, supporting ground operations where they could still contribute effectively. This decision essentially conceded the strategic bombing campaign to the Allies, who could now attack German industry with relative impunity, while Germany could not meaningfully retaliate. The psychological impact of this technological revelation extended beyond immediate tactical implications. German military leadership, political authorities, and industrial managers had operated throughout the war's early years under assumptions about German technological superiority that the Norden Bombsight contradicted. Germany was supposed to possess the world's finest optical industry, the most advanced mechanical engineering, the best-trained technical workforce. These were not empty propaganda claims, but beliefs grounded in Germany's genuine pre-war leadership in precision manufacturing, scientific research, and technical education. Yet here was unmistakable evidence that American industry had achieved sophistication, matching or exceeding German capabilities, while simultaneously operating at scale Germany could not approach. The cognitive dissonance this created was profound. How had the Americans, whom German propaganda portrayed as culturally inferior and technologically backward, achieved such capability? The uncomfortable answer was that German assessments of American industrial capacity had been catastrophically wrong, based on outdated pre-war data and wishful thinking rather than realistic intelligence. American industrial mobilization for war had transformed manufacturing capacity at a pace and scale unprecedented in history. The arsenal of democracy that President Roosevelt had promised in December 1940 was becoming reality by 1943. Liberty ships were being launched at rates exceeding one per day. Aircraft production had grown from fewer than 6,000 per year in 1939 to over 96,000 in 1944. Tank production would exceed 88,000 vehicles in 1943 and 1944 combined. This was not just quantity. As the Norden Bombsight demonstrated, American industry was simultaneously achieving quality that matched or exceeded anything Germany produced. The strategic calculus was inescapable. Germany faced enemies who collectively possessed overwhelming industrial superiority and were progressively translating that superiority into military advantage across every domain. In the air, American precision bombing and British night area bombing were systematically destroying German industrial capacity. At sea, Allied shipbuilding had overcome U-boat sinkings, making the Atlantic secure for the vast military buildup that would eventually enable invasion of Western Europe. On land, Soviet industrial production, sustained by American Lend-Lease and by factories relocated beyond German reach, was producing tanks and artillery in quantities that German forces could not match. Several Luftwaffe officers who attended the June 30th conference later recorded their impressions in diaries and memoirs. General Lieutenant Adolf Galland, who would become General der Jagdflieger, General of Fighter Forces in November 1941 and served in that role through January 1945, wrote extensively about German aviation's declining situation. While his published memoirs do not specifically mention the Norden Bombsight conference, his writings from mid-1943 consistently emphasized themes of Allied technological and numerical superiority, overwhelming German tactical advantages. Galland described watching American bomber formations approaching German targets in daylight at altitudes. German fighters struggled to reach effectively, protected by increasing numbers of long-range escort fighters, delivering bombs with accuracy that destroyed specific buildings within factory complexes. The contrast with Germany's situation fighters increasingly flying defensively, unable to protect German cities or industries effectively, facing enemies who seemed to possess unlimited aircraft, and pilots created profound demoralization even among the most dedicated officers. The Norden Bombsight examination occurred during a period when multiple technological revelations were simultaneously undermining German confidence. Just months earlier, in February 1943, examination of the captured British cavity magnetron had revealed that Allied radar technology was years ahead of German capabilities. That discovery explained mysterious U-boat losses and Allied aircraft detection capabilities that German theory had declared impossible. Now the Norden Bombsight revealed similar superiority in precision instrument manufacturing and mechanical computing. What other technological surprises might the Allies deploy? This uncertainty bred caution that sometimes paralyzed decision-making. When intelligence reported possible Allied developments, proximity fuses for anti-aircraft shells, jet aircraft, atomic weapons, German leadership had to consider that these reports might be accurate given previous surprises. Resources were diverted to countermeasure programs against threats that might or might not exist. Research programs pursued multiple redundant approaches because confidence in German technological assessment had been shaken. The psychological warfare value of genuine technological superiority extended beyond the weapon's direct military utility. German attempts to reverse engineer and manufacture copies of the Norden Bombsight followed a pattern similar to the cavity magnetron experience. Engineers could understand the operating principles. Laboratories could manufacture individual components meeting specifications, but translating laboratory capability into production capacity proved impossible given resource constraints and competing priorities. By late 1943, German optical manufacturers had produced several prototype bombsights incorporating some Norden design principles, particularly improved gyroscopic stabilization and automatic tracking mechanisms. These prototypes, tested at Rechlin and at operational bomber units, showed performance improvements over standard Lot 7 equipment. However, they remained substantially less capable than captured Norden units. More problematically, manufacturing cost and complexity were approximately 3 times higher than standard equipment. Luftwaffe procurement authorities, facing demands to maximize production of existing proven equipment rather than introducing new designs requiring tooling changes and worker retraining, declined to order production. The improved bomb sights remained experimental curiosities, occasionally installed in specialized aircraft, but never reaching general service. This pattern repeated across numerous German programs, attempting to match Allied technological advantages. Improved radar systems, better aircraft engines, more capable radio equipment in each case. German engineers could design superior systems and build prototypes, but production remained constrained by industrial capacity limits, material shortages, and the disruption caused by Allied bombing of the very factories needed to manufacture new equipment. Germany was trapped in a vicious cycle where Allied technological superiority enabled bombing that prevented Germany from developing counters to that technological superiority. The human dimension of precision bombing manifested in German civilian casualties and industrial worker experiences. American precision bombing doctrine targeted military and industrial objectives, not civilian populations per se. However, the distinction between military and civilian targets blurred in practice. Workers lived near factories. Bomb aiming, despite Norden bombsight accuracy, remained imperfect under combat conditions. Attacking a ball-bearing factory in a city inevitably caused casualties among surrounding residential areas. German propaganda exploited these casualties, portraying American precision bombing as terror attacks on civilians, indistinguishable from RAF night area bombing. The reality was more nuanced. American bombardiers genuinely attempted to hit specific industrial targets and frequently succeeded with accuracy that minimized collateral damage relative to tonnage delivered. But modern industrial warfare made civilian immunity impossible. The workers manufacturing tanks, the engineers designing aircraft, the managers coordinating production, all were legitimate military targets under the logic of total war, even though they were technically non-combatants. The strategic bombing campaign's effectiveness remained controversial during the war and continues debated by historians. German industrial production actually increased through 1943 and into 1944 despite bombing, leading some analysts to conclude strategic bombing failed to achieve its objectives. However, this increase occurred from a lower baseline than would have existed without bombing. German industries continually diverted resources to repair bomb damage, disperse facilities, and protect against future attacks. The counterfactual question, how much more could Germany have produced without bombing, is impossible to answer definitively, but evidence suggests bombing constrained production substantially below potential. More measurably, strategic bombing forced Germany to divert enormous resources to air defense. By 1944, approximately 1 million German personnel operated anti-aircraft defenses, including operating flak batteries, maintaining equipment, and supporting infrastructure. These personnel might otherwise have served in combat roles on the eastern or western fronts. Aircraft production increasingly emphasized fighters for defense rather than bombers for offense. ammunition production dedicated substantial capacity to anti-aircraft shells. The cumulative effect was to impose costs on Germany that exceeded the direct damage bombing inflicted. The Norden Bombsight examination at Rechlin became one data point in German military intelligence's broader assessment of Allied capabilities and intentions. Throughout summer and fall 1943, intelligence staffs compiled comprehensive evaluations of enemy strengths across all domains. The conclusions painted an increasingly bleak picture. Allied material superiority was overwhelming and growing. Allied technological capabilities equaled or exceeded German performance in most areas and were superior in several critical domains, including radar, computing, and industrial manufacturing processes. Most troublingly, Allied advantages were not static. American aircraft production was introducing new models with improved performance at rates German production could not match. B-17 and B-24, bombers that had been marginally protected by defensive armament in 1942, were being supplemented and eventually replaced by models with improved turrets, more guns, and better armor. P-38, P-47, and especially P-51, escort fighters with progressively extended range, were making deep penetration bombing raids less costly, allowing sustained attacks on targets previously protected by distance. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now and don't forget to subscribe.